Section 8.2, Systems of Linear Equations in Three Variables. An equation of the form ax plus by plus cz equals d, where a, b, and c are real numbers such that a, b, and c are not all zero, is a linear equation in three variables, x, y, and z. A solution of a system of linear equations in three variables is an ordered triple of real numbers that satisfies all equations of the system. The solution set of the system is the set of all its solutions. Example 1. Show that the ordered triple, -1, -4, 5, is a solution of the system. The three variables are in the order x, y, and z respectively. We'll substitute that point into each of the three equations. Starting with the first equation, we substitute it in and we see that we get a true value. So we move on to the second equation, and again we get a true value. We substitute our values into the third equation, and it works out to be true. So the ordered triple satisfies the three equations, and therefore the ordered triple is a solution of the system. Let's look at a procedure for solving a system of linear equations in three variables. The first step is to reduce the system of three equations, three unknowns, to a system of two equations and two unknowns. With that system of two equations, we'll reduce it down to one equation with one unknown and solve for that variable. We then take that variable back to either of the equations we had in step 2 to solve for a second variable. We then take the two variables that we found in steps 2 and 3 and substitute them into any of our original equations to find the remaining variable. And then we finish by checking our proposed solution in each of the original equations. Example 2. Solve this system with three variables. The first step is to turn this system of three equations, three unknowns into a system of two equations, two unknowns. So we need to look at our equations to try to eliminate a variable. We can eliminate z by taking the top two equations and adding them together. X plus 3x is 4x. 4y plus 2y is 6y. The z's cancel and the constants add to 28. Next, we need to look at another combination of equations and eliminate z again. The top equation and bottom equation are close. If we double the top equation, the z's will cancel. So we'll add 2 times equation 1 plus equation 3. Equation 3 is unchanged. We multiply the first equation by 2, so that gives us a 2x plus 8y minus 2z equals 40. Adding them together, the x terms add to 4x, the y terms add to 5y, the z terms cancel, and the constant terms add to 24. We now take these two equations and take them to our next step, which is to solve the resulting system. If we leave the top equation alone and multiply the bottom equation by -1, then our x terms will cancel. Adding up, we get y equals 4, and that's already solved for y, so we move on to step 3. For step 3, we back substitute the y equals 4 into either of our two equations. We'll take this top one, substitute in the 4, simplify, and subtract 24 from both sides, and then divide both sides by 4, and we get x equals 1. So now we take that x equals 1 and y equals 4 that we found in the previous steps, and we back substitute into any of our original equations. These are our choices. We'll start with this top one. We substitute in the 1 and the 4 for x and y respectively. Simplify, subtract 17 from both sides, and divide both sides by -1, and we get z equals -3. So our proposed solution is x is 1, y is 4, and z is -3. And if we substitute those values in for x, y, and z into each of the three original equations, we'll see that it checks out. So this is our solution set. Example 3. Find the quadratic function y equals ax squared plus bx plus c whose graph passes through these points. We begin by substituting each ordered pair into the equation y equals ax squared plus bx plus c. For the point 1, 4, we substitute in and we simplify, and we get the equation 4 equals a plus b plus c. For the point 2,1, we substitute and simplify, and we get 1 equals 4a plus 2b plus c. And for the point 3,4, we substitute, simplify, and we get 4 equals 9a plus 3b plus c. We now will take these three equations into the next step. Those three equations become this system of three equations and three unknowns. So we need to reduce this system to a system of two equations and two unknowns. We can eliminate c by taking equations 1 and 2. We keep one equation the same and multiply the other one by -1. And when we add them together, the c's will cancel. This resulting equation will become part of our system of two equations, two unknowns. So we need a second equation. We can eliminate c from equations 1 and 3 by multiplying one of them by -1. So then when we add, the c's will cancel again, giving us a second equation. Now we'll take these two equations to our next step. We can solve this resulting system of two equations and two unknowns by multiplying the top equation by -2 and keeping the bottom equation the same. With the bottom equation the same, we can cancel out the b terms because -2 times -3a is a positive 6a, a -2 times a negative b is a positive 2b, and a -2 times the 3 is a -6. Adding together, the b's cancel, we get -2a equals -6. Dividing both sides by -2 gives us a equals 3. And that's one of our values. We now back substitute a equals 3 into either of these two equations. We simplify, add 9 to both sides, and then divide both sides by -1, giving us b equals -12. Now that we know a and b, we can find c. We substitute the a and b that we found in the previous step into any of these original equations. We substitute, we simplify, add 9 to both sides, and we get c equals 13. We now take the three values that we found and we place them into the quadratic y equals ax squared plus bx plus c, where we found a to be 3, b was -12, and c is 13. So the equation for the quadratic function whose graph passes through these 3 points is y equals 3x squared minus 12x plus 13.